Hello, in this video I want us to practice how to perform functional group transformations for compounds involving an ether, thiol, sulfide, and even disulfide. So the first thing I want us to do is to learn some of the methods by which you can synthesize an ether. An ether can be synthesized on industrial scale if we use concentrated sulfuric acid in the presence of heat. So this is called acid catalyzed dehydration. So it requires the formation of water which needs to be removed as the reaction proceeds. And again, this requires 2 times the alcohol so that we end up forming the symmetrical ether. The problem with this reaction is we cannot use it to synthesize an ether which is not symmetrical. For example, if we are planning to synthesize an ether where one of the alkyl substituents is a propyl, another one is an ethyl, then we use what is called Williamson ether synthesis. In Williamson ether synthesis, we use a strong base that can deprotonate an alcohol like sodium hydride, followed by an alkyl halide. Like here, to install the propyl group, we can use propyl iodide to form the product. Another method of synthesizing ethers is a modification of oxymercuration demercuration, where we could use, say, mercury acetate followed by ethanol, ETOH, instead of water, and then we use sodium borohydride to do demercuration. So instead of forming the alcohol in the more substituted position, well, like an OH, we are going to install the ethoxy group in the more substituted position. So the ethoxy group ends up giving us an ether. Okay. Now, what kind of other reactions could we do? Once we form an ether, we can be able to do what is called an acid-promoted cleavage. So if we react this with excess HBr and heat, what we are going to form is going to be this product, an OH, plus it's going to regenerate the alkyl halide. So here we have Br. Okay. Same thing is going to happen over here. Now remember that I've given you the mechanism for this process in the lecture notes. So the reverse process involves an SN2. So here we are going to form the alcohol because we cannot do an SN2. The nucleophile, the bromine nucleophile, cannot be able to do an SN2 on a tertiary position. However, if we use the primary positions here, we can be able to form Br plus 1, 2, 3 Br. Okay. Now, moving on, we know we can be able to transform an alcohol into an alkyl halide, like in this case to a bromide, if we use, say, PBr3, that is phosphorus tribromide, or we could be able to transform this into a good living group if we use, for example, tosyl chloride with pyridine followed by, say, sodium bromide. So we can use that, or phosphorus tribromide gives us the product in one step, and then we end up with the alkyl halide. Once we form the alkyl halide, or if we just have a starting material as an alkyl halide, then we can use sodium hydrosulfide, which is NaSH. Here the hydrosulfide is going to act as a nucleophile and be able to attack this carbon, so we end up forming a thiol. A thiol can then undergo a reaction similar to Williamson ether synthesis, but what you need to know is thiols have a pKa of approximately 10. So therefore we do not need sodium hydride. We can just use sodium hydroxide, whose conjugate acid has a pKa of roughly 16, 15.7 to be specific. So that means it can be able to deprotonate the thiol. So in the first step, then in the second step, we can use propyl iodide to form the product. It's also possible to transform thiol into a disulfide. And this reaction requires the use of, actually it's just one step. So just use bromine solution in water together with sodium hydroxide, and that requires 2 times of the thiol so that we can generate the product. Another type of reaction we can look at is with a sulfide. Sulfides can easily undergo oxidation, especially if you use a strong oxidizing agent like hydrogen peroxide. Then it transforms into what we call a sulfone, S-U-O-N-E. It transforms into a sulfone. If we use something like sodium periodate, sodium periodate can transform it into a sulfoxide. Okay. The sulfoxide, in this case, this is dimethyl sulfoxide, DMSO, which is a very widely used solvent, especially in biological experiments. So with the sulfoxide, sulfoxide can easily help to do what is called oxidative cleavage in the presence of ozone. So we can end up with a product that looks like this. You should have done this earlier in 331. So this is just kind of a review. So we end up with an aldehyde and a ketone. The sulfide here usually acts as an alkylating agent. So if you have a nucleophile like cyanide or any nucleophile that could be able to attack an electrophile and have a carbon-carbon bond formed, then the sulfide helps to do an alkylation. So in the presence of methyl bromide, the sulfide is able to react with an alkyl halide to form an intermediate. Once it forms this intermediate, then now any nucleophile could be able to attack the alkyl that is attached to the sulfide, and then it actually ends up installing that alkyl halide to the nucleophile, and it regenerates the sulfide plus a salt, which is sodium bromide in this case. So these are some of the kind of reactions you need to know in this chapter. But again, we can do multi-step synthesis. For example, could actually ask you to start, for example, from an alcohol and follow this route all the way to that and all the way to a disulfide. So I could start from an alcohol and ask you to synthesize this compound. You should know how to play around with the multi-step synthesis. Here is an example of a multi-step synthesis. So we do have an alkyl halide as a starting material, and we want to form this complex ether. Okay? So the first step would be to think of how do we perform this kind of transformation. Well, with the presence of the halide, we can actually form a carbon-carbon bond if we transform the alkyl halide into a Grignard reagent. Now, this is a trick. Anytime you see two carbon atoms and an oxygen, the culprit is an epoxide. Okay? The culprit is an epoxide. So if we use ring opening to give us the two carbon atoms and we end up with an alcohol here, then you might be tempted to think that, well, with an alcohol, we can be able to use an alkyl halide. Okay, so we can remove the proton using sodium hydride, then we use the nucleophile here to attack that position. Now the problem is that is tertiary, so that reaction is not going to work. No SN2 on a tertiary position. So the best way would be to transform the alcohol into an alkyl halide. So we could transform it into like a bromine group if we use phosphorus tribromide, and then instead of using the alkyl halide here, we can transform that into a tert-butanol. That way, we are going to be doing an SN2 on a primary carbon. Alright, so now that we know the strategy, let us put it down. So the first step is Grignard reagent. And then after that we use an epoxide followed by a source of proton to form and then we transform the alcohol into an alkyl halide. And then we need the tert-butanol in the presence of sodium hydride. That's going to give us tert-butoxide. And that's the one that's going to be able to attack and kick out the bromide group. And then we end up with the product.